You know how engineers can simulate the insane amount of heat flowing through a computer chip before they even build the thing? Or how they know with absolute certainty a new bridge design will hold up? The secret isn't just raw computing power. It's this beautiful and frankly mind-bending area of math called functional analysis. And we're going to see how it works by building the whole idea from scratch. So here's our game plan. First, we're going to completely blow up the idea of what a vector can be. Then, we'll invent a ruler to measure these new vectors. After that, we'll need a protractor to find their angles. Then, we'll forge a tool to deal with the messy, sharp-edged problems you find in the real world. And finally, we'll put it all together and watch this toolkit solve something that seems totally impossible. All right, our first step is the big one. This is a mental leap, but it's the foundation for everything that follows. We're going to learn to see an entire, complete function as just a single object, a single point. Let's start on familiar ground. Think back to high school physics or math. A vector, right? It's just an arrow. It lives in 2D or 3D space, it has a length, and it points somewhere. Simple. This is our home base.
Now, here's where mathematicians did what they do best. They generalized it. They came up with a set of rules for a vector space. And here's the crucial bit. They realized that anything that follows these basic rules, you can add them and you can stretch or shrink them, can be called a vector. The arrow is just the most famous example. And that right there opens up a whole universe of possibilities.
Okay, now let's look at something totally different. This is not a simple arrow. This is a continuous function. You can imagine this curve showing the temperature at every single point along the edge of a CPU. It holds a literally infinite amount of information. And here it is. This is the wild idea. What if we could treat that entire infinitely detailed curve as a single thing, a single dot in some huge, new, infinite dimensional space? That's the core concept. Every single possible temperature curve is now just one point in our new function space. So, we've got this incredible new space filled with functions. Great, but what can we do there? Well, the first thing you need in any space is a way to measure stuff. We need a ruler.
It's the natural question, isn't it? If this whole function is now a vector, what in the world does length or size even mean? I mean, how do you measure a curve?
Well, we can use an analogy. For that simple arrow, we find its length using the good old Pythagorean theorem. Mathematicians call that the Euclidean norm. So for a function, we can just invent a new ruler. We could say, for instance, that its size is just its highest peak. That's called the maximum norm. The big idea is we get to define the right ruler, the right norm, for whatever problem we're trying to solve. Okay, tool 1, the ruler, is in our toolkit. We can measure a function's size. But what about the relationship between two different functions? To figure that out, we're going to need a way to measure angles. And that brings us to the Hilbert space. Think of this as our function space, but with a serious upgrade. The killer new feature is a tool called a scalar product, and what it lets you do is pretty amazing. It lets you define the angle between two entire functions. It's a way of measuring how similar they are, or how aligned they are in this crazy abstract space. The most famous example of this in action is the Fourier series. It's a brilliant idea. You start with any complex, messy function. Think of a sound wave. The magic is that you can project that function onto a set of simple, pure waves, like sines and cosines. These projections become your coordinates. They tell you, you need this much of sine wave A and this much of cosine wave B. And with that simple recipe, you can rebuild the original complex function perfectly. So far, we've been playing with nice, smooth functions. But you know, reality is messy. It's got sharp corners and abrupt changes. And this is where traditional calculus kind of hits a brick wall. Just take a look at the simple function y equals the absolute value of x. It looks fine, right? Except for that one sharp point right at the bottom. And believe me, corners like this pop up everywhere in physics and engineering. If you ask a first-year calculus student, hey, what's the slope, the derivative, at that exact point? They'll tell you it's undefined. The slope from the left is -1, the slope from the right is +1. So at the corner itself, calculus just gives up. Our standard tool is broken. This is where mathematicians got incredibly clever. They invented something called the weak derivative. Instead of trying to find the slope at one impossible point, it sort of zooms out and looks at the function's average behavior around that point. This new definition just sails right over those sharp corners. And this tool is the heart of something called a Sobolov space, a workshop custom built to handle the jagged, messy functions that actually describe reality. All right, we've assembled our toolkit. We can treat functions like points, we have rulers for them, we have protractors, and we can even take their derivatives when they're not smooth. Now for the grand finale. Let's solve the problem we started with. Let's go back to that computer chip. Finding the final stable temperature pattern across its surface is a classic and really hard engineering problem. In math terms, it's called solving Poisson's problem. The goal sounds simple enough. Out of an infinite number of possible heat patterns, we need to find the one and only one function that actually satisfies the laws of physics for our chip. And here's where it all clicks. Engineers take this complicated physical problem with all its real-world messiness and they rephrase it inside a Sobolev space. That lets them use all our new tools, the norms, the inner products, the weak derivatives, to set the stage for one final, heroic move. That move is applying a powerhouse result called the Riesz representation theorem. For an engineer, this theorem is basically a mathematical guarantee. It says, look, if you frame your problem correctly in this special space, a single, unique, stable solution doesn't just probably exist, it is guaranteed to exist. All that infinite complexity just collapses into one certain answer. No guesswork. And this isn't just for computer chips. This is the hidden engine that powers so much of our world. The finite element analysis that designs bridges and planes, the simulations that model entire galaxies, the signal processing that makes our phones and Wi-Fi work. It's everywhere. It really makes you wonder, doesn't it? The big lesson from all this is that sometimes the hardest problems only seem impossible because we're looking at them in the wrong space. The moment we find the right perspective, the solution becomes clear. So what other impossible problems are out there, just waiting for us to find the right way to see them?